Hello there. I'm so glad you found your way here tonight. Wherever you are in the world right now, allow yourself to settle into the shared moment of stillness. Let the noise of the day fade away. Let your thoughts grow quiet, like the gentle drift of stars across the endless dark. Right now, as you listen to these words, something extraordinary stretches above you. An infinite expanse of space filled with planets, stars, galaxies, and mysteries we have only begun to understand. And somehow, from all that cosmic vastness, you are here, listening, wondering. Tonight, we journey outward, into the quiet realm of space itself. A universe of black holes, distant worlds, and phenomena that defy our everyday understanding. We will explore how the universe can expand faster than light, how some planets rain diamonds, how time itself bends near the most massive objects in existence, all of it waiting to be shared in the stillness. Tonight, let's drift off together while exploring over 100 soothing facts about space. There's no rush here, no test at the end. Just soft words and quiet wonders to carry you into rest. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the vast cosmos that surrounds us all. Either way, this space is for you. There is something profoundly peaceful about contemplating the universe. Every fact about space is a reminder that we are part of something far greater than ourselves. And it is always expanding, always evolving, always creating new stories written in starlight. You are part of this story. The oxygen in your lungs was forged in ancient stars. The iron in your blood was born in supernova explosions. The atoms that make your cells have been part of nebulae, planets, and creatures that lived billions of years before you were born. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in, let your breathing slow, and let the weight of the day drift away like starlight fading into the cosmic background. Space is patient beyond measure. Galaxies form over billions of years without haste. Stars burn for eons before fading into white dwarfs. Black holes wait at the centers of galaxies, patient and eternal. And yet, within all that steadiness, there are sudden bursts of wonder. Supernovae that outshine entire galaxies. Collisions that reshape trillion stars. Cosmic jets that stretch for millions of light years. Tonight, we will wander through this magnificent outer world. We will meet the forces that shape the cosmos and discover processes that determine the fate of everything that exists. And we will uncover truths about space that may surprise even the most curious minds. But there is no hurry. The universe has been expanding for nearly 14 billion years. It can wait a little longer while you rest. Let us begin with the fundamental nature of our expanding cosmos. The universe can expand faster than the speed of light. Einstein's theory of special relativity tells us that nothing can travel through space faster than light, yet the universe itself plays by different rules. The fabric of space-time can stretch and expand without violating this cosmic speed limit, because it is not matter moving through space, but rather space itself growing larger. Distant galaxies are receding from us at velocities that exceed the speed of light, not because they are moving, but because the space between us and them is expanding at an ever-accelerating rate. This phenomenon is driven by dark energy, a mysterious force that pushes galaxies apart and causes the expansion of the universe to accelerate over time. the most distant objects we can observe are already moving away from us faster than light, which means that any light they emit today will never reach us. The observable universe is therefore shrinking in a sense, as more and more galaxies cross the threshold beyond which their light cannot outpace the expansion. Space itself has a subtle background glow from the Big Bang. When you look at a television screen tuned to static, a small fraction of that noise is actually radiation left over from the very beginning of the universe. This faint glow, known as the cosmic microwave background, permeates all of space and represents the cooled remnant of the immense heat generated during the Big Bang nearly 14 billion years ago. When the universe was only about 380,000 years old, it had cooled enough for atoms to form and for light to travel freely through space for the first time. That ancient light has been traveling ever since, stretched by the expansion of space from visible light into microwave radiation. Scientists have mapped this background glow in exquisite detail, revealing tiny temperature fluctuations that eventually gave rise to all the galaxies, stars, and planets we see today. The cosmic microwave background is the oldest light in the universe, a snapshot of the cosmos when it was still in its infancy. It serves as powerful evidence for the Big Bang theory and provides a window into the earliest moments of existence. We can hear the echo of the universe's birth. The cosmic microwave background is sometimes described as the afterglow of the Big Bang, but in a sense it can also be translated into sound waves that represent the acoustic oscillations of the early universe. Before atoms formed, the young universe was filled with a dense plasma of particles and radiation, and pressure waves rippled through this cosmic soup, much like sound waves travel through air. These primordial oscillations left their imprint on the distribution of matter and radiation, creating patterns that scientists can detect in the cosmic microwave background today. By analyzing these patterns, astronomers have reconstructed what the universe sounded like in its first moments, revealing deep bass notes far below the range of human hearing. These cosmic sounds were generated by matter falling into regions of higher density and bouncing back due to radiation pressure, creating a kind of universal heartbeat. The study of these acoustic peaks has allowed scientists to measure the age, composition, and geometry of the universe with remarkable precision. In a very real sense, we can listen to the echo of creation itself. The edge of the observable universe is moving away from us. The observable universe is the portion of the cosmos from which light has had time to reach us since the Big Bang, stretching roughly 46 billion light-years in every direction. This edge is not a physical boundary, but rather a horizon beyond which we cannot see, because light from those regions has not yet had time to arrive. Due to the accelerating expansion of the universe driven by dark energy, this cosmic horizon is effectively receding from us at an ever-increasing rate. Galaxies near the edge are being carried away so quickly that the light they emit today will never reach Earth. The observable universe is therefore a sphere of visibility centered on our location, but the actual universe may extend far beyond what we can ever hope to observe. Every year, more galaxies slip beyond this horizon, lost to us forever as the expansion of space outruns the speed of light. The universe continues to grow larger, while our view of it becomes increasingly limited, a humbling reminder of the vastness beyond our reach. Space can stretch and shrink without anything moving. One of the most counterintuitive aspects of modern physics is that space itself is not a passive backdrop, but an active participant in the drama of the universe. According to general relativity, space-time can be stretched, compressed, and warped by the presence of mass and energy. This means that distances between objects can change, even if neither object is moving through space in the traditional sense. During the expansion of the universe, galaxies are not flying apart through space, but rather the fabric of space between them is stretching, carrying them along for the ride. Similarly, near massive objects like black holes, space becomes compressed and distorted, affecting everything within it. Gravitational waves, ripples in space-time caused by violent cosmic events, represent another way in which space itself can undulate and oscillate. These waves stretch and squeeze space as they pass, momentarily changing the distances between objects without anything physically moving. The dynamic nature of space is one of the most profound insights of modern cosmology. The universe was once smaller than an atom. In the very first moments after the Big Bang, all the matter, energy, and space-time that would eventually become the observable universe was compressed into an unimaginably tiny point. This primordial state, sometimes called a singularity, was smaller than a single atom and hotter than anything that has existed since. Within a fraction of a second, a period known as cosmic inflation caused this minuscule speck to expand exponentially, growing from subatomic scales to something larger than a galaxy in an instant. This rapid expansion smoothed out the universe and set the stage for the formation of matter, atoms, stars, and eventually galaxies. The idea that everything we see around us, every star, every galaxy, every planet, was once packed into something smaller than the nucleus of an atom, is almost impossible to comprehend. Yet this is the picture that emerges from our best understanding of cosmology and particle physics. The universe began in a state of extreme compression and has been expanding and cooling ever since. Dark energy is pushing the universe apart. For most of cosmic history, scientists believed that gravity from all the matter in the universe would eventually slow down and perhaps reverse the expansion that began with the Big Bang. However, in the late 1990s, observations of distant supernova revealed something astonishing. The expansion of the universe is not slowing down but accelerating. This acceleration is attributed to dark energy, a mysterious form of energy that permeates all of space and exerts a repulsive gravitational effect. Dark energy makes up roughly 68% of the total energy content of the universe. Yet its fundamental nature remains one of the greatest unsolved mysteries in physics. Unlike ordinary matter and radiation, dark energy does not dilute as the universe expands, but maintains a constant density, causing its influence to grow over time. As dark energy continues to dominate, the expansion of the universe will accelerate ever faster, eventually pushing galaxies so far apart that the night sky will grow dark and empty. The fate of the cosmos is intimately tied to this enigmatic force that we can detect but do not yet understand. The Milky Way is surrounded by a halo of invisible matter. Our galaxy floats within an enormous sphere of dark matter that extends far beyond the visible disk of stars and gas. This dark matter halo is roughly 10 times more massive than all the stars, planets, and gas in the Milky Way combined, yet it emits no light and cannot be seen directly. We know it exists because of the gravitational influence it exerts on visible matter, causing stars at the outer edges of the galaxy to orbit faster than they would if only visible matter were present. Without this dark matter scaffolding, galaxies like the Milky Way would fly apart because there would not be enough gravitational pull to hold them together. The halo extends hundreds of thousands of light-years from the galactic center, enveloping the entire galaxy in an invisible cocoon of matter. Dark matter particles rarely interact with ordinary matter, except through gravity, passing through planets and stars without effect. This ghostly presence shapes the structure of our galaxy and determines its fate within the cosmic web. Some galaxies are made almost entirely of dark matter. Astronomers have discovered a class of galaxies that appear to be composed almost exclusively of dark matter, with very few visible stars relative to their total mass. These ultra-diffuse galaxies are so faint that they were only detected in recent years using advanced telescopes and imaging techniques. Despite their ghostly appearance, they contain as much mass as the Milky Way, with dark matter accounting for more than 99% of their content. How these galaxies formed with so little ordinary matter remains a puzzle that challenges our understanding of galaxy formation. Some theories suggest that early supernovae or interactions with larger galaxies stripped away most of their gas before it could form stars. Others propose that these dark matter-dominated galaxies represent a primordial population that formed differently from typical galaxies. The existence of such objects demonstrates that the universe contains structures far stranger than our own star-filled neighborhood, hidden in the cosmic darkness. Dark matter shapes the movement of galaxies across the cosmos. On the largest scales, the universe is organized into a vast cosmic web of filaments, walls, and voids, with galaxies clustered along the densest strands of this structure. Dark matter is the invisible architect of this web, providing the gravitational framework around which ordinary matter collects and forms galaxies. Without dark matter, galaxies would not have formed as quickly after the Big Bang, because ordinary matter alone could not collapse fast enough against the outward pressure of radiation. Dark matter clumped together first, creating gravitational wells into which ordinary matter fell, eventually igniting into stars and assembling into galaxies. The motion of galaxies within clusters and superclusters is governed by the distribution of dark matter, which outweighs visible matter by a factor of roughly 5-to-1. By mapping the movements of galaxies, astronomers can infer the presence and distribution of dark matter throughout the universe. This invisible substance is the cosmic scaffolding upon which the entire structure of the universe is built. Black holes can fire jets millions of light-years long. Some of the most energetic phenomena in the universe occur when supermassive black holes at the centers of galaxies actively consume surrounding material. As matter spirals into these cosmic drains, it heats up to millions of degrees and generates powerful magnetic fields that channel some of the infalling material into twin jets of plasma. These jets shoot outward from the poles of the black hole at speeds approaching the speed of light, extending far beyond the host galaxy into intergalactic space. The largest of these jets stretch for millions of light-years, dwarfing the galaxies that produce them and carrying more energy than millions of stars combined. These relativistic jets can influence the formation of stars in distant galaxies, heating the surrounding gas and preventing it from collapsing. The mechanism by which black holes produce such focused and powerful outflows is still not fully understood, but it involves the complex interplay of gravity, magnetism, and rotation. These cosmic searchlights are visible across billions of light-years and represent some of the most impressive displays of energy in the cosmos. Some black holes spin nearly at the speed of light. Black holes are not static objects, but can rotate at extraordinary speeds, dragging the fabric of spacetime around them like a whirlpool dragging water. The fastest spinning black holes approach the theoretical maximum rotation rate, with their event horizons moving at velocities close to the speed of light. This rotation has profound effects on the surrounding spacetime, creating a region called the ergosphere, where nothing can remain stationary and everything must move in the direction of the spin. The angular momentum of a spinning black hole can be extracted and converted into energy, a process that may power some of the most luminous objects in the universe. Black holes acquire their spin from the material they consume and the mergers they undergo with other black holes. Measurements of black hole spin provide insights into the history of these objects and the processes that formed them. Near the edge of a rapidly spinning black hole, space-time itself twists and warps in ways that challenge our understanding of physics. The largest black holes are billions of times more massive than the Sun. At the hearts of most large galaxies lurk supermassive black holes, gravitational monsters that contain millions to billions of solar masses within their event horizons. The largest known black holes are so massive that their event horizons would encompass our entire solar system, swallowing everything from the Sun out to the orbit of Pluto and beyond. These cosmic giants grew over billions of years by consuming stars, gas, and smaller black holes, as well as by merging with other supermassive black holes during galaxy collisions. Despite their immense size, supermassive black holes are surprisingly difficult to detect because they emit no light themselves. We find them by observing the behavior of stars and gas that orbit close to the galactic center, moving at speeds that reveal the presence of an invisible massive object. The relationship between supermassive black holes and their host galaxies is still being unraveled, but it appears that these giants play a crucial role in shaping galactic evolution. The most massive black holes represent the ultimate endpoints of matter concentration in the universe. Entire stars can be eaten by black holes. When a star wanders too close to a black hole, the immense gravitational forces can tear it apart in a violent event known as a tidal disruption. The side of the star nearest the black hole experiences much stronger gravity than the far side, stretching the star into a long ribbon of superheated gas. Some of this stellar material spirals into the black hole, forming a temporary accretion disk that glows brilliantly across the electromagnetic spectrum. These tidal disruption events can outshine entire galaxies for weeks or months before fading as the stellar debris is consumed. Astronomers have observed dozens of such events, each providing valuable insights into black hole behavior and stellar structure. The rate at which stars are devoured depends on the density of stars near the galactic center and the mass of the central black hole. For the unfortunate star, the encounter represents a spectacular but final journey, as its remains are swallowed forever behind the event horizon. Some black holes are surrounded by swirling disks of fire. When material falls toward a black hole, it does not plunge straight in, but instead forms a spinning accretion disk around the event horizon. Friction within this disk heats the infalling gas to temperatures of millions of degrees, causing it to glow brilliantly in X-rays and other high-energy radiation. These accretion disks are among the most luminous objects in the universe, sometimes outshining all the stars in their host galaxy combined. The inner edge of the disk orbits at incredible speeds, approaching a significant fraction of the speed of light as it spirals ever closer to the point of no return. Magnetic fields threading the disk can become twisted and amplified, helping to launch the powerful jets that some black holes produce. The study of accretion disks has revealed much about the behavior of matter under extreme conditions, serving as natural laboratories for testing the physics of extreme gravity. These fiery halos are the calling cards of actively feeding black holes throughout the cosmos. Stars can be torn apart by tidal forces near black holes. The gravitational field near a black hole is so steep that different parts of an approaching object experience vastly different gravitational pulls. This difference creates tidal forces that stretch objects along the direction of the black hole and squeeze them perpendicular to that direction, a process poetically called spaghettification. For stellar mass black holes, this stretching would occur outside the event horizon, tearing apart anything that approached too closely. For supermassive black holes, the tidal forces at the event horizon are actually quite gentle, meaning an astronaut could cross the threshold without being torn apart, at least initially. However, as they fell deeper into the black hole, the tidal forces would eventually become overwhelming. The strength of tidal forces depends on the mass of the black hole and the distance from its center, with smaller black holes producing more extreme effects near their event horizons. These tidal forces are responsible for some of the most violent and energetic events observed in the universe. The universe is full of wandering black holes. Not all black holes remain anchored to galaxies or star systems. Some stellar mass black holes are ejected from their host galaxies through gravitational interactions or the asymmetric kicks they receive during supernovae. These rogue black holes drift through intergalactic space, invisible and solitary, carrying their gravitational influence with them. Estimates suggest that the Milky Way alone may contain hundreds of millions of stellar mass black holes, many of which are not bound to binary systems and simply wander through the galaxy. Rogue supermassive black holes can also be created when galaxies merge, and the resulting gravitational dance ejects one of the central black holes. These wandering giants carry billions of solar masses through the cosmic void, potentially encountering other galaxies or stars along the way. Detecting these invisible travelers is extremely difficult, but occasionally their presence is revealed when they pass in front of a background star, and their gravity bends the light in a phenomenon called gravitational microlensing. Black holes can merge into even larger black holes. When two black holes orbit each other, they gradually lose energy by emitting gravitational waves, ripples in the fabric of space-time that carry energy away from the system. Over millions or billions of years, this causes their orbits to shrink until they eventually spiral together and merge in a cataclysmic event. The final moments of a black hole merger release more energy than all the stars in the observable universe combined, though this energy is carried away as gravitational waves rather than light. The resulting black hole is typically larger than either of its parents, though some mass is lost during the merger as gravitational radiation. Scientists have detected dozens of black hole mergers using gravitational wave observatories, opening a new window onto these previously invisible events. These observations have revealed black holes in surprising mass ranges and configurations, challenging our understanding of how they form. The cosmic population of black holes grows ever larger through this process of hierarchical merging. Time moves differently in strong gravity. One of the most remarkable predictions of Einstein's general relativity is that time does not flow at the same rate everywhere in the universe. Near massive objects where gravity is stronger, time passes more slowly compared to regions where gravity is weaker. This effect, known as gravitational time dilation, has been confirmed by experiments using precise atomic clocks at different altitudes on Earth. A clock at sea level runs slightly slower than one on a mountaintop because it is deeper in Earth's gravitational well. Near extreme objects like neutron stars or black holes, this effect becomes dramatic, with time slowing to a crawl compared to distant observers. An astronaut hovering near a black hole would age much more slowly than their colleagues waiting far away, experiencing what might feel like hours while years pass for the rest of the universe. This bending of time is not an illusion but a fundamental property of how gravity warps the fabric of space-time itself. A black hole's gravity can slow time to a crawl. The gravitational time dilation effect reaches its most extreme manifestation near the event horizon of a black hole. As an observer falls toward a black hole, time for them passes normally from their own perspective, but to a distant observer watching the descent, the falling person appears to slow down as they approach the event horizon. From the outside, the infalling observer would seem to freeze at the boundary of the black hole, their image growing ever dimmer and redder as the light they emit is stretched by the immense gravity. In theory, it would take an infinite amount of external time for the observer to actually cross the event horizon, though from the falling observer's perspective, they would pass through in a finite time. This paradox illustrates how profoundly black holes warp our understanding of space and time. At the event horizon, time effectively stops from the perspective of the external universe, creating a frozen boundary that light itself cannot escape. Time may flow differently in other parts of the universe. Because time is affected by both gravity and motion, different regions of the universe may experience time at different rates, depending on their local conditions. Regions with higher concentrations of matter, such as galaxy clusters, would experience slightly slower time than voids where matter density is low. If the universe contains regions beyond our observable horizon with vastly different properties, time might flow at radically different rates in those distant domains. The expansion of the universe itself affects the relationship between time and distance, complicating our understanding of simultaneity across cosmic scales. When we observe distant galaxies, we see them as they were billions of years ago, looking back through time as well as across space. This connection between time and space is so fundamental that physicists often speak of space-time as a single unified entity rather than separate concepts. The cosmos may contain pockets where time behaves in ways we cannot directly experience from our local perspective. Light from distant stars can bend around massive objects. General relativity predicts that mass warps the fabric of spacetime, and light traveling through this curved spacetime follows bent paths rather than straight lines. This phenomenon, known as gravitational lensing, was first confirmed during a solar eclipse in 1919, when the apparent positions of stars near the Sun were observed to shift slightly. Massive objects like galaxies and galaxy clusters can act as cosmic magnifying glasses, bending and focusing light from objects behind them, and sometimes producing multiple distorted images. The most dramatic examples include Einstein rings, where a distant galaxy appears as a complete ring of light around a foreground massive object. Gravitational lensing has become a powerful tool for astronomers, allowing them to detect dark matter, measure the masses of distant objects, and observe galaxies that would otherwise be too faint to see. Microlensing by individual stars can temporarily brighten background objects, revealing the presence of planets, and even rogue black holes. The bending of light is a direct consequence of the curvature of spacetime around massive objects. The speed of light is the ultimate cosmic speed limit. In a vacuum, light travels at approximately 300,000 kilometers per second, and according to special relativity, nothing with mass can ever reach or exceed this velocity. As an object with mass accelerates toward the speed of light, it requires ever more energy to accelerate further, with the energy requirement approaching infinity as it gets closer to light speed. This is not a limitation of our technology, but a fundamental property of spacetime itself. Massless particles like photons always travel exactly at the speed of light, while particles with mass are forever confined to slower velocities. The speed of light also represents the maximum speed at which information or causality can travel through the universe, setting a fundamental limit on communication across cosmic distances. Even gravity propagates at the speed of light, meaning that gravitational influences cannot travel faster than electromagnetic radiation. This cosmic speed limit shapes the structure of cause and effect throughout the universe. Some stars are so large, they would swallow our solar system whole. The largest stars in the universe are hypergiants, stellar behemoths so vast that if placed at the center of our solar system, their surfaces would extend beyond the orbit of Jupiter or even Saturn. These stars are typically red supergiants or hypergiants, evolved stars in the final stages of their lives that have expanded to incredible sizes. While our Sun has a diameter of about 1.4 million kilometers, the largest known stars span more than 2 billion kilometers across. Despite their enormous volumes, these giant stars are relatively diffuse, with densities lower than the air we breathe at sea level. The outer layers of these stars are so tenuous that there is no clear boundary between the star and the surrounding space. These stellar titans burn through their nuclear fuel rapidly, living fast and dying spectacularly in supernova explosions. Their sheer scale challenges our intuitions about what a star can be, reminding us of the extremes the universe can produce. The largest known star could hold millions of Earths inside it. Volume scales with the cube of radius, which means that the largest stars contain truly staggering amounts of space within their tenuous outer layers. A star like Stephenson 218, one of the largest currently known, has a radius more than 2,000 times that of the Sun. If this star replaced the Sun at the center of our solar system, its surface would extend past the orbit of Saturn. Within such a volume, you could fit billions of Earths and still have room to spare, though the star's actual mass is only tens of times greater than the Sun because of its low density. These enormous stars are near the end of their evolutionary journeys, having exhausted the hydrogen in their cores and expanded while burning heavier elements. The title of largest known star changes as astronomers discover and measure more distant objects, but the scale of these cosmic giants remains consistently mind-boggling. Our Sun, by comparison, is a modest yellow dwarf, utterly dwarfed by these stellar monsters. Some stars burn so hot, they could vaporize you instantly. While our Sun has a surface temperature of about 5,500 degrees Celsius, the hottest stars blaze at temperatures exceeding 200,000 degrees. These blue hypergiants and Wolf-Rayet stars emit most of their energy in the ultraviolet and X-ray parts of the spectrum, radiating so intensely that they drive powerful stellar winds that strip away their outer layers. At such extreme temperatures, atoms are completely ionized, existing as a plasma of free electrons and atomic nuclei. Approaching one of these stars would be instantly fatal, with any spacecraft or astronaut vaporized long before reaching the stellar surface. The radiation environments around hot stars are so intense that planets orbiting nearby would be sterilized of any potential life. These hottest stars are also among the most massive and short-lived, burning through their nuclear fuel in just a few million years before exploding as supernovae. Their intense heat makes them some of the most luminous objects in any galaxy. Some stars are powered by helium instead of hydrogen. Most stars spend the majority of their lives fusing hydrogen into helium in their cores. But this is only the first stage of stellar nuclear burning. When a star exhausts its core hydrogen supply, it can begin fusing helium into heavier elements like carbon and oxygen, if it is massive enough. This helium burning phase represents a significant change in the star's structure, often causing it to expand into a red giant or supergiant. The process requires much higher temperatures than hydrogen fusion, typically exceeding 100 million degrees Celsius at the core. Helium burning produces less energy per unit mass than hydrogen burning, so stars pass through this phase relatively quickly. In the most massive stars, nuclear fusion continues to build heavier elements up through iron, at which point no further energy can be extracted and the star collapses. Each stage of nuclear burning represents a step along the stellar life cycle, transforming the star's composition and structure as it ages. There are stars that change color as they age. A star's color is directly related to its surface temperature, with hotter stars appearing blue or white and cooler stars appearing orange or red. As stars evolve over their lifetimes, their temperatures and therefore their colors can change dramatically. A star like our Sun currently shines yellow-white, but in about 5 billion years it will swell into a red giant, cooling its surface and shifting its light toward the red end of the spectrum. After shedding its outer layers, it will eventually become a white dwarf, a dense remnant that starts off extremely hot and blue-white before gradually cooling over trillions of years. Massive stars can undergo even more dramatic color changes, cycling between blue supergiant and red supergiant phases as they evolve. Some variable stars change color on timescales of days or weeks due to pulsations that alter their surface temperatures. The color of a star tells astronomers about its current temperature, age, and evolutionary state. Neutron stars spin so fast they warp space around them. When a massive star collapses at the end of its life, it can form a neutron star, an incredibly dense remnant, only about 20 kilometers across, but containing more mass than the Sun. The conservation of angular momentum causes these collapsed cores to spin at astonishing rates, with some neutron stars completing hundreds of rotations every second. At such speeds, the equator of a neutron star can move at a significant fraction of the speed of light, creating extreme relativistic effects. The rapid rotation combined with the intense gravitational field warps space-time around the neutron star, creating a complex gravitational environment. This relativistic spinning also powers the emission of electromagnetic radiation from the magnetic poles, producing the lighthouse-like beams that make pulsars detectable. The fastest spinning neutron stars, known as millisecond pulsars, have been spun up by accreting matter from a companion star. These cosmic gyroscopes are among the most stable rotators in the universe, serving as precise cosmic clocks. A single spoonful of neutron star material would weigh billions of tons. Neutron stars achieve densities that are almost impossible to comprehend, packing more than the mass of the Sun into a sphere the size of a city. At such densities, matter behaves in ways completely unlike anything we experience on Earth, with atoms crushed together until only neutrons remain. A teaspoon of neutron star material would weigh approximately 6 billion tons, roughly equivalent to the weight of a mountain compressed into a tiny volume. This extreme density results from the gravitational collapse overcoming all normal forces that keep matter puffed up, squeezing out all empty space between particles. The pressure at the core of a neutron star is so intense that scientists still debate exactly what form matter takes there, with possibilities including exotic states like quark matter. Neutron stars represent the densest form of matter that can exist before collapsing entirely into a black hole. These cosmic anvils are laboratories for physics at its most extreme. Some stars are so dense they defy imagination. White dwarfs, neutron stars, and the theoretical quark stars represent progressively denser states of stellar remnants, each pushing the limits of how tightly matter can be compressed. A white dwarf, the remnant of a star like our Sun, is about the size of Earth but contains roughly half a solar mass, making it incredibly dense compared to ordinary matter. Neutron stars take this to extremes, with densities exceeding that of an atomic nucleus throughout their volume. If there was something slightly denser than a neutron star, it might be a quark star, where neutrons themselves have broken down into their constituent quarks. Beyond a certain density threshold, gravity wins completely, and the object collapses into a black hole from which nothing can escape. These compact objects represent the endpoints of stellar evolution for stars of different masses. The study of dense stellar remnants provides insights into the fundamental physics of matter under extreme conditions. A neutron star's magnetic field can shred atoms. Neutron stars possess the most powerful magnetic fields in the known universe, with some reaching strengths trillions of times greater than Earth's magnetic field. These extreme magnetic fields arise from the compression of the parent star's magnetic field during the collapse, concentrating magnetic flux into a tiny volume. A special class of neutron stars called magnetars has magnetic fields so intense that they would be lethal from thousands of kilometers away. At such field strengths, the magnetic force on atoms becomes stronger than the electromagnetic forces holding them together, causing atoms to stretch into elongated shapes or break apart entirely. Even empty space near a magnetar is affected, with the vacuum itself becoming birefringent and polarizing light that passes through. These magnetic monsters occasionally release enormous bursts of energy in starquakes, producing gamma-ray flares that can be detected across the galaxy. The magnetic fields of neutron stars represent some of the most extreme conditions in the universe. Astronomers have detected planets around pulsars. The first exoplanets ever confirmed were not found around normal stars but orbiting a pulsar, the spinning remnant of a supernova explosion. These pulsar planets were discovered in the early 1990s by detecting tiny variations in the timing of the pulsar's radio pulses caused by the gravitational tug of orbiting bodies. The discovery was surprising because any planets that existed before the supernova should have been destroyed or ejected by the explosion. Scientists believe these worlds may have formed from the debris disk left behind after the supernova, essentially second-generation planets born from the death of a star. Life on such worlds would be extremely unlikely due to the intense radiation environment around pulsars, which bathe their surroundings in deadly X-rays and particles. Despite their inhospitability, pulsar planets demonstrate that planetary formation can occur in the most unexpected circumstances. These strange worlds represent some of the most unusual planetary systems ever discovered. Massive stars can collapse in seconds. After millions of years of nuclear burning, a massive star reaches a point where iron accumulates in its core, and fusion can no longer release energy. In just a fraction of a second, the core collapses from roughly the size of Earth to just a few dozen kilometers across, falling inward at a quarter of the speed of light. This catastrophic implosion happens so quickly that the outer layers of the star have no time to react before the core rebounds and sends a shockwave racing outward. The entire process, from the beginning of core collapse to the launch of the supernova explosion, takes less than a second. During this brief moment, the collapsing core releases more energy in the form of neutrinos than the Sun will produce in its entire lifetime. The speed of this collapse stands in stark contrast to the millions of years the star spent steadily burning through its nuclear fuel. A star that lived for eons ends its life in the blink of a cosmic eye. A single supernova can outshine an entire galaxy. At the peak of its brightness, a supernova can emit as much light as all the billions of stars in its host galaxy combined. This incredible luminosity results from the enormous amount of energy released during the explosion, equivalent to what the Sun will radiate over its entire 10 billion-year lifetime, compressed into just a few weeks. Type Ia supernovae, which result from the thermonuclear detonation of white dwarf stars, are particularly consistent in their peak brightness, making them valuable tools for measuring cosmic distances. Core collapse supernovae from massive stars can be even more energetic, though their brightness varies more depending on the mass and composition of the progenitor star. Historical supernovae have been bright enough to be visible in broad daylight and cast shadows at night. The most distant supernovae can be detected across billions of light-years, serving as cosmic beacons that illuminate the expansion history of the universe. These stellar deaths are among the most spectacular displays of energy in the cosmos. New planets can be born from the ashes of exploded stars. Supernovae scatter heavy elements forged inside stars across interstellar space, enriching the gas and dust from which new generations of stars and planets will form. Before the first stars exploded, the universe contained only hydrogen, helium, and trace amounts of lithium, with heavier elements being completely absent. Every atom of carbon, oxygen, silicon, and iron in the universe was created either inside stars or during supernova explosions. When a massive star explodes, it seeds its surroundings with these heavier elements, which eventually become incorporated into new molecular clouds. As these enriched clouds collapse to form new stars, the leftover material forms a protoplanetary disk from which planets can coalesce. Earth and all its life forms are built from atoms that were once inside another star that exploded billions of years ago. We are quite literally made of stardust, the recycled remnants of stellar deaths. Some stars explode without warning. While astronomers can predict that certain stars are nearing the end of their lives based on their evolutionary stage, the precise moment of a supernova remains impossible to forecast. The core collapse that triggers a massive star's explosion happens on a timescale of seconds, far too quickly for any warning signs to propagate to the surface. Similarly, Type Ia supernovae occur when white dwarfs in binary systems accrete enough mass to trigger runaway thermonuclear fusion, a threshold that can be crossed suddenly. Stars that appear stable one day can explode the next, transforming from ordinary points of light into brilliant cosmic fireworks. Some supernovae have been detected in galaxies that were being observed for completely unrelated reasons, catching astronomers by surprise. The unpredictable nature of supernovae means that continuous monitoring of the sky is essential for detecting these events early. Every night, automated surveys scan the heavens, hoping to catch stars in the act of exploding. Some stars' dying collapses are so violent they twist space-time. When the core of a massive star collapses to form a neutron star or black hole, the process generates gravitational waves that ripple outward through the fabric of space-time. These waves carry information about the asymmetries in the collapse, encoding details about the dying star's final moments. If the collapse is particularly asymmetric, or if a neutron star forms with a rapidly rotating non-spherical shape, the gravitational wave emission can be substantial. In cases where the core collapses directly into a black hole, the space-time distortions are even more extreme. Gamma-ray bursts, among the most energetic events in the universe, are thought to occur when highly magnetized jets form during certain stellar collapses, accompanied by intense gravitational wave emission. The combination of gravitational wave observatories and traditional telescopes allows astronomers to study these violent deaths from multiple perspectives. The universe rings with gravitational waves from stellar collapses happening throughout the cosmos. Some stars flicker like cosmic lighthouses. Pulsars, the rapidly rotating neutron stars mentioned earlier, emit beams of radiation from their magnetic poles that sweep through space like the rotating beacon of a lighthouse. When one of these beams happens to point toward Earth, we detect a regular pulse of radio waves, X-rays, or even visible light. The rotation rates of pulsars are remarkably stable, making them some of the most precise natural clocks in the universe. Some pulsars rotate thousands of times per second, their beams flickering faster than the human eye could perceive. The regularity of pulsar signals is so precise that they can be used to detect gravitational waves, measure distances, and even test theories of physics. The first pulsar was discovered in 1967, and initially the regular signal was so unexpected that astronomers briefly considered whether it might be an alien communication. Today we know of thousands of pulsars scattered throughout our galaxy, each one a cosmic lighthouse, marking the grave of a massive star. Some stars pulse like beating hearts. Certain types of variable stars physically expand and contract in regular cycles, brightening and dimming in predictable patterns that resemble a cosmic heartbeat. Cepheid variables are among the most famous of these pulsating stars, growing larger and cooler over periods of days to weeks before shrinking back and heating up. The relationship between a Cepheid's pulsation period and its intrinsic brightness makes these stars invaluable distance indicators for measuring the size of galaxies and the expansion of the universe. Other pulsating stars include RR Lyrae variables, which helped establish the size of the Milky Way, and Mira variables, which can change in brightness by a factor of 1,000 or more. The pulsations are driven by the interaction between energy flowing outward from the star's core and layers in the stellar atmosphere that become more opaque as they heat up. This cosmic push and pull creates sustained oscillations that can last for millions of years. These stellar hearts beat in rhythms that astronomers have learned to read as cosmic yardsticks. There are stars that appear to blink out of existence. Eclipsing binary stars are systems where two stars orbit each other in such a way that one periodically passes in front of the other, as seen from Earth. When the brighter star is eclipsed by its dimmer companion, the total light from the system drops noticeably, creating the appearance that the star has suddenly dimmed or blinked out. The famous star Algol in the constellation Perseus has been known as the demon star for centuries because of its mysterious periodic dimming, later explained by this eclipse mechanism. By studying the pattern and depth of eclipses, astronomers can determine the relative sizes, masses, and temperatures of stars in binary systems with remarkable precision. Some eclipsing binaries show both primary and secondary eclipses depending on the relative brightness of the two stars. These cosmic dances provide valuable insights into stellar properties that would be difficult to measure for single stars. The apparent blinking of these stars reveals the hidden choreography of gravitationally bound stellar pairs. Stars can swap material with their neighbors. In close binary star systems, gravitational interactions can cause material to flow from one star to another in a process called mass transfer. When one star expands to fill its Roche lobe, the teardrop-shaped region where its gravity dominates, gas from its outer layers can stream toward the companion star. This transferred material often forms an accretion disk around the receiving star, spiraling inward and heating up to produce bright emission. Mass transfer can dramatically alter the evolution of both stars, rejuvenating older stars with fresh fuel, or pushing white dwarfs toward the critical mass needed to trigger a supernova. In some systems, the mass transfer is so vigorous that the stars become enveloped in a common envelope of shared material. These interacting binaries produce some of the most energetic and variable phenomena observed in stellar astronomy. The gravitational intimacy of close binary stars creates cosmic relationships that profoundly affect their individual destinies. Some stars are on collision courses with each other. In dense stellar environments like the cores of globular clusters, stars can pass close enough to one another that gravitational interactions send them on collision courses. When two stars merge, the result depends on their masses and types, but can range from a single larger star to an explosive event that destroys one or both participants. Blue straggler stars, found in many old star clusters, are thought to be the products of stellar mergers, appearing younger and more massive than their ancient companions. In extreme cases, the disruption caused by close encounters can eject stars from clusters entirely, sending them flying through the galaxy at high velocities. Computer simulations suggest that stellar collisions and near misses are relatively common in the dense cores of some clusters, occurring perhaps once every few thousand years. When neutron stars or black holes merge, the collision produces gravitational waves detectable across the universe. These cosmic fender benders reshape the populations of stars in crowded environments. Entire galaxies can hide in almost complete darkness. Ultra-diffuse galaxies are ghostly collections of stars that are spread so thinly across space that they are nearly invisible against the cosmic background. Despite having diameters comparable to the Milky Way, these faint galaxies may contain only a fraction of a percent as many stars, making them extremely difficult to detect. Many ultra-diffuse galaxies were only discovered in the last decade as telescope technology improved enough to reveal their faint glow. Some of these dim galaxies appear to be dominated almost entirely by dark matter, with very little ordinary matter-forming stars. Others may be the remnants of normal galaxies that lost most of their gas through interactions with the hot medium in galaxy clusters. The existence of these dark and diffuse galaxies suggests that the visible population of galaxies represents only part of the galactic diversity in the universe. Countless ghost galaxies may lurk in the darkness between the bright spirals and ellipticals we usually study. The Milky Way and Andromeda are doomed to collide. Our nearest large galactic neighbor, the Andromeda Galaxy, is currently racing toward the Milky Way at approximately 400,000 kilometers per hour. In about 4 to 5 billion years, the two galaxies will meet in a cosmic collision that will transform both into a single larger galaxy. Despite the dramatic imagery this evokes, individual stars are so far apart that direct collisions between them will be extremely rare during the merger. Instead, the gravitational interaction will distort both galaxies, pulling out long tidal tails of stars and gas, triggering bursts of new star formation, and eventually reshaping the merged system into an elliptical or peculiar galaxy. The supermassive black holes at the centers of both galaxies will eventually spiral toward each other and merge, releasing enormous amounts of gravitational wave energy. By the time this collision occurs, our Sun will be in its later stages of evolution, though any future Earthlings watching will witness night skies dramatically different from our own. This cosmic dance has already begun, with Andromeda and the Milky Way bound by gravity and destined to become one. Entire galaxies can merge into one. Galaxy mergers are among the most transformative events in cosmic evolution, reshaping the structure and star-forming activity of the participants over hundreds of millions of years. When two large galaxies collide, their mutual gravity strips stars from their original orbits, creating chaotic streams and shells of debris. Gas within the galaxies is compressed by tidal forces and shocks, often triggering intense bursts of star formation that light up the merging system. The central supermassive black holes of both galaxies sink toward the center of the new combined system, eventually merging and releasing gravitational waves. After the merger is complete, the result is typically an elliptical galaxy, a smooth collection of old red stars, with little remaining gas for future star formation. Every large galaxy in the universe has likely experienced multiple mergers throughout its history, growing and evolving through these cosmic unions. The violence of galactic collisions ultimately builds the largest and most massive galaxies we observe today. Some galaxies contain trillions of stars. While the Milky Way contains an estimated 2 to 400 billion stars, the largest galaxies in the universe dwarf our home by an enormous margin. Giant elliptical galaxies found at the centers of massive galaxy clusters can contain several trillion stars, accumulated over billions of years of mergers and accretion. These supergiant galaxies are among the most massive bound structures in the cosmos, with total masses including dark matter that can exceed 100 trillion solar masses. The largest known galaxies span millions of light-years, making the Milky Way seem modest by comparison. These stellar giants typically reside in the dense cores of galaxy clusters, where they continue to grow by cannibalizing smaller galaxies that fall into their gravitational embrace. Despite their enormous stellar populations, giant elliptical galaxies are often relatively dim because they contain mostly old red stars with little active star formation. Each of these cosmic metropolises represents the accumulated history of countless smaller galaxies now merged into a single vast system. There are galaxies that spin in the opposite direction to most others. In most spiral galaxies, stars orbit the galactic center in a consistent direction determined by the angular momentum of the primordial cloud from which they formed. However, astronomers have discovered galaxies with unusual rotation patterns, including some with counter-rotating disks, where different populations of stars orbit in opposite directions. These bizarre configurations typically arise from mergers or interactions with other galaxies, wherein falling material brings angular momentum oriented differently from the existing disk. In some cases, a galaxy may have acquired gas from a neighbor that happened to be rotating in the opposite sense, forming new stars that orbit contrary to the original population. Counter-rotating galaxies provide valuable insights into the merger history and evolution of galactic systems. The study of these unusual rotators helps astronomers understand how galaxies grow and change through cosmic time. These cosmic contrarians demonstrate that galactic dynamics can be far more complex than simple rotation. Some galaxies are shaped like perfect rings. Ring galaxies are among the most visually striking objects in the universe, appearing as bright circles of stars surrounding relatively empty centers. These unusual shapes are typically created when a smaller galaxy punches through the center of a larger disk galaxy at high speed, sending a ripple of density outward like a stone dropped in a pond. As this wave propagates, it triggers intense star formation along the expanding ring, lighting it up with young blue stars while the center remains sparse. The famous Cartwheel Galaxy is a spectacular example, displaying a brilliant blue ring of newborn stars surrounding its disturbed core. Ring galaxies are relatively rare because they require a nearly head-on collision with precise geometry, meaning only a small fraction of galaxy interactions produce this distinctive shape. The ring phase is also temporary, lasting only a few 100 million years, before the galaxy settles into a more normal configuration. These cosmic halos are beautiful snapshots of galactic violence frozen in time. Our Sun is just one of hundreds of billions of stars in the Milky Way. The Milky Way is a vast spiral galaxy containing an estimated 200 to 400 billion stars, each one a sun in its own right, with the potential to host planets and perhaps life. Our Sun orbits the galactic center at a distance of about 26,000 light-years, taking roughly 230 million years to complete a single orbit. From our position within the galactic disk, we see the combined light of billions of distant stars, as the Milky Band that stretches across the night sky. Despite the enormous number of stars in the Milky Way, the distances between them are so vast that the galaxy is mostly empty space. The nearest star to the Sun, Proxima Centauri, is over 4 light-years away, a distance that would take tens of thousands of years to cross with current spacecraft technology. Each star in the galaxy has its own story, whether it is a young blue giant burning bright and fast, or an ancient red dwarf that will shine for trillions of years. Our Sun is an ordinary yellow dwarf, unremarkable among the multitude yet special to us. The Milky Way smells of rum and tastes of raspberries. Astronomers studying the molecular clouds at the center of our galaxy have detected ethyl formate, a chemical compound that gives rum its distinctive smell and contributes to the flavor of raspberries. This organic molecule is just one of many complex chemicals found floating in the vast clouds of gas and dust between stars. The interstellar medium contains hundreds of different molecular species, ranging from simple molecules like water and carbon monoxide to complex organic compounds that include amino acids and sugars. These discoveries suggest that the building blocks of life are not rare but rather common throughout the galaxy, formed in the cold depths of molecular clouds. Radiotelescopes detect these molecules by their characteristic spectral signatures, allowing astronomers to effectively taste and smell the cosmos from a distance. The chemistry occurring in interstellar space is remarkably rich, producing substances that we associate with food, drink, and even life itself. While you could never actually sample these cosmic flavors, the galaxy is suffused with familiar scents and tastes. There are rivers of stars in the Milky Way. Scattered throughout the Milky Way are stellar streams, elongated chains of stars that trace out arcs and curves across the sky like rivers of light. These streams are the remnants of dwarf galaxies and globular clusters that were captured and torn apart by the Milky Way's gravitational forces. As these smaller systems orbit within our galaxy, tidal forces stretch them into long filaments of stars that maintain coherent motion even as they disperse. Some stellar streams wrap around the Milky Way multiple times, providing valuable information about the distribution of dark matter in our galaxy. The most famous streams include the Sagittarius Stream, the debris of a dwarf galaxy that is still being devoured by the Milky Way. By studying these stellar rivers, astronomers can reconstruct the merger history of our galaxy and trace the paths of long-gone satellite systems. The Milky Way is not a static entity, but one that continues to grow by consuming smaller companions. The Milky Way is moving through space at incredible speed. Although we perceive no sense of motion in our daily lives, the Earth, solar system, and entire Milky Way galaxy are all hurtling through space at tremendous velocities. The Earth orbits the Sun at about 30 kilometers per second, while the Sun orbits the galactic center at roughly 220 kilometers per second. On even larger scales, the Milky Way itself is moving at approximately 600 kilometers per second relative to the cosmic microwave background radiation. This motion appears to be directed toward a massive concentration of galaxies known as the Great Attractor, a region of gravitational influence that is pulling our local group of galaxies along with many others. Beyond even this, our galaxy is part of a larger flow of matter toward even more massive structures in the cosmic web. Despite these enormous velocities, the distances involved are so vast that the motion is imperceptible on human timescales. We are cosmic travelers moving through the universe at speeds that dwarf our fastest rockets. The Andromeda Galaxy is already visible to the naked eye. On a clear dark night, far from city lights, you can look up and see the Andromeda Galaxy as a faint fuzzy patch in the constellation of the same name. This smudge of light represents the most distant object visible to the unaided human eye, located approximately 2.5 million light-years from Earth. What you are seeing is the combined glow of roughly 1 trillion stars, a galaxy even larger than our own Milky Way. The light reaching your eyes tonight left Andromeda around the time our distant ancestors first began to walk upright in Africa. For most of human history, stargazers noticed this mysterious nebulous spot without knowing what it truly was. Only in the 20th century did astronomers confirm that Andromeda is an island universe of stars, a galaxy similar to our own adrift in the cosmic sea. Gazing at Andromeda is one of the most humbling experiences available to anyone with clear skies and a moment of wonder. Saturn could float in a large enough ocean. Despite being the second largest planet in our solar system, Saturn has an average density lower than that of water. If you could find an ocean large enough, Saturn would theoretically float on its surface like a giant cosmic cork. This remarkably low density results from Saturn's composition, which is dominated by hydrogen and helium in gaseous and liquid forms without a large rocky core, Saturn would have to be about 760 times larger than Earth to contain a planet of Saturn's volume, making such an ocean physically impossible. The low density also contributes to Saturn's visibly flattened shape, with the planet bulging noticeably at the equator due to its rapid rotation. Saturn completes a day in just over 10 hours, spinning so fast that its equatorial diameter is about 10% larger than its polar diameter. This combination of low density and rapid rotation makes Saturn one of the most distinctively shaped planets in our solar system. Saturn's rings are slowly disappearing. The iconic rings of Saturn are not permanent features, but rather temporary decorations that are slowly raining down onto the planet itself. Tiny ice particles in the rings become charged by solar radiation and plasma, causing them to spiral inward along Saturn's magnetic field lines and fall into the atmosphere as ring rain. Scientists estimate that enough material is falling from the rings to fill an Olympic-sized swimming pool every half hour. At this rate, the entire ring system may vanish within about 100 million years, a blink of an eye in cosmic terms. The rings may also be younger than previously thought, perhaps only 100 million years old, rather than dating back to Saturn's formation. This would mean that dinosaurs walking the Earth would have seen a ringless Saturn in the night sky. Future generations may need to appreciate these beautiful rings while they still exist, as Saturn will eventually become just another ordinary-looking gas giant. The hottest planet in the solar system is not the closest to the Sun. Despite Mercury being the closest planet to the Sun, Venus holds the record for the highest surface temperature in our solar system. Venus averages about 465 degrees Celsius at its surface, hot enough to melt lead, while Mercury's day side reaches only about 430 degrees. The difference is due to Venus's thick atmosphere, which is composed almost entirely of carbon dioxide and creates an extreme greenhouse effect. Sunlight passes through the Venusian atmosphere and heats the surface, but the thermal radiation trying to escape back to space is trapped by the dense carbon dioxide blanket. Mercury, by contrast, has almost no atmosphere to retain heat, so its dark side plunges to extremely cold temperatures, while only the sunlit side becomes hot. The lesson of Venus is that atmospheric composition matters enormously for planetary climate, a fact with profound implications for understanding Earth's own sensitivity to greenhouse gases. Venus serves as a cautionary tale of planetary heating taken to extremes. A day on Venus lasts longer than its year. Venus rotates extremely slowly on its axis, taking about 243 Earth days to complete a single rotation, while it orbits the Sun in only 225 Earth days. This means that a Venusian solar day, the time from one sunrise to the next, is longer than the planet's year. To add to the strangeness, Venus rotates in the opposite direction from most planets, meaning that the Sun rises in the west and sets in the east. Scientists believe that Venus may have been struck by a large object early in its history, flipping it upside down or slowing its rotation to a near standstill. The extremely slow rotation contributes to the planet's extreme heat distribution, with the dense atmosphere efficiently transferring heat from the day side to the night side. Despite the bizarre timekeeping, the thick clouds of Venus mean that any observer on the surface would rarely see the Sun anyway. Venus is a world where time seems to move at a different pace. Mars has the tallest volcano in the solar system. Olympus Mons on Mars is the largest and tallest volcano in the solar system, rising approximately 22 kilometers above the surrounding plains. This shield volcano is so massive that it dwarfs any volcanic structure on Earth, with a base diameter roughly the size of France. The relatively low gravity on Mars allowed the volcano to grow to such heights without collapsing under its own weight. Unlike Earth, Mars lacks plate tectonics, so volcanic hotspots could remain fixed in place, allowing magma to pile up in one location over billions of years. The caldera at the summit of Olympus Mons is large enough to contain entire metropolitan areas, with cliffs around its edges that drop 3 kilometers to the surrounding terrain. Evidence suggests that Olympus Mons erupted relatively recently in geological terms, perhaps within the last few 100 million years, and may not be entirely extinct. This colossal volcanic mountain stands as a testament to the extreme geological features that can develop on other worlds. There are storms on Jupiter bigger than Earth. The Great Red Spot on Jupiter is an anticyclonic storm so large that the entire planet Earth could fit inside it with room to spare. This massive storm has been raging for at least 400 years, since it was first observed through early telescopes in the 17th century. Wind speeds within the Great Red Spot reach up to 400 kilometers per hour, faster than any hurricane on Earth. Despite its longevity, the storm has been observed to be shrinking over the past century, and scientists are uncertain how long it will continue to persist. Jupiter's turbulent atmosphere hosts numerous other storms and atmospheric features, though none are as dramatic or long-lived as the Great Red Spot. The energy that drives these storms comes from Jupiter's internal heat and rapid rotation, rather than from the Sun. These swirling tempests are visible from telescopes on Earth, providing a window into the violent atmospheric dynamics of gas giant planets. Jupiter's magnetic field is immensely powerful. Jupiter possesses the strongest magnetic field of any planet in our solar system, roughly 20,000 times more powerful than Earth's. This enormous magnetic field is generated by electrical currents flowing through liquid metallic hydrogen deep within Jupiter's interior. The magnetosphere of Jupiter, the region of space dominated by its magnetic field, extends millions of kilometers into space and even reaches the orbit of Saturn in the direction opposite the Sun. This vast magnetic bubble traps charged particles from the solar wind and volcanic material from the Moon Io, creating deadly radiation belts that would be lethal to unprotected humans. Spacecraft visiting Jupiter must be specially hardened to survive the intense radiation environment near the planet. The interaction between Jupiter's magnetic field and its moons creates complex electrical currents and spectacular aurora at the planet's poles. Jupiter's magnetosphere is the largest single structure in the solar system after the heliosphere. There are planets made almost entirely of gas. Gas giant planets like Jupiter and Saturn are composed primarily of hydrogen and helium, with no solid surface on which a spacecraft could land. As you descend into a gas giant's atmosphere, the gas gradually becomes denser and hotter, eventually transitioning into liquid and then into exotic states like liquid metallic hydrogen, without ever encountering a definite boundary. These planets may have small rocky or metallic cores at their centers, but the vast majority of their volume is dominated by gaseous and liquid hydrogen. Despite being called gas giants, much of Jupiter's interior is actually liquid, under the tremendous pressures found deep within the planet. The outer atmospheres display complex weather patterns, including bands of clouds, violent storms, and powerful jet streams. Gas giants are common throughout the galaxy, with many exoplanets discovered in the hot Jupiter category, orbiting close to their stars. These fluffy worlds represent a fundamentally different type of planet from the rocky terrestrial bodies like Earth. Some planets have rings more magnificent than Saturn's. While Saturn's rings are the most famous in our solar system, astronomers have discovered exoplanets with ring systems that dwarf Saturn's by enormous margins. The exoplanet J1407b possesses a ring system more than 600 times larger than Saturn's, with rings that would span a significant fraction of the distance between Earth and the Sun if placed in our solar system. These supersized rings were detected when the planet passed in front of its host star, causing complex patterns of dimming that revealed the multiple ring structure. If J1407b's rings were around Saturn, they would be easily visible from Earth and would dominate the night sky when the planet was above the horizon. Closer to home, all 4 giant planets in our solar system have ring systems, though Jupiter, Uranus and Neptune's rings are much fainter and less spectacular than Saturn's. Ring systems are likely common around giant planets throughout the galaxy, formed from debris of shattered moons or captured material. The universe may contain ring systems of breathtaking beauty that we have yet to discover. The Sun's atmosphere is hotter than its surface. One of the most puzzling aspects of solar physics is that the Sun's outer atmosphere, known as the corona, is vastly hotter than its visible surface. The photosphere, the surface we see, has a temperature of about 5,500 degrees Celsius, while the corona reaches temperatures of 1 to 3 million degrees. This seems to violate common sense, as you would expect temperature to decrease as you move away from the heat source. Scientists have proposed several mechanisms to explain this coronal heating problem, including energy transfer through magnetic waves and the reconnection of magnetic field lines. Recent observations from solar probes flying close to the Sun are providing new data to help solve this decades-old mystery. The corona is visible during total solar eclipses as a pearly white halo surrounding the blocked Sun. Understanding why the corona is so hot remains one of the central questions in solar physics. The Sun's light takes 8 minutes to reach Earth. Despite traveling at the fastest speed possible in the universe, light still takes approximately 8 minutes and 20 seconds to cover the 150 million kilometers from the Sun to Earth. This means that when you look at the Sun, you are seeing it as it was more than 8 minutes ago, not as it is at this exact moment. If the Sun were to suddenly vanish, we would continue to see its light and feel its gravity for over 8 minutes before noticing anything was wrong. This light travel time is measured in a unit called the astronomical unit, which astronomers use as a standard measure for distances within the solar system. The delay in sunlight reaching Earth is minuscule compared to the time light takes to cross interstellar distances, but it still represents a fundamental disconnect between what we observe and what currently exists. The sunlight warming your face right now left the Sun before you took your last few breaths. Every view of the cosmos is a view into the past. The Sun will one day become a white dwarf. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin the final stages of its evolution. It will first expand into a red giant, growing so large that it may engulf the inner planets including Mercury and Venus, and possibly Earth as well. After shedding its outer layers into a beautiful planetary nebula, the core will be left behind as a white dwarf, a dense ember about the size of Earth, but containing roughly half the Sun's original mass. White dwarfs shine from residual heat rather than nuclear fusion, slowly cooling over trillions of years until they fade into cold, dark remnants called black dwarfs. The universe is not yet old enough for any black dwarfs to exist, as even the oldest white dwarfs are still cooling. The fate of the Sun is shared by most stars in the universe, which will end their lives as white dwarfs rather than in supernova explosions. Our Sun's distant future is as a slowly dimming cosmic cinder. The northern lights are caused by solar winds. The aurora borealis in the northern hemisphere and aurora australis in the south are produced when charged particles from the Sun interact with Earth's magnetic field and atmosphere. The solar wind, a constant stream of electrons and protons flowing outward from the Sun, occasionally intensifies during solar flares and coronal mass ejections. When these particles reach Earth, they are funneled by the magnetic field toward the polar regions, where they collide with atmospheric gases and cause them to glow. Different gases produce different colors, with oxygen creating green and red aurora, while nitrogen contributes blue and purple hues. The dancing lights of the aurora can extend across vast portions of the sky, creating curtains and ribbons of shimmering color. During periods of intense solar activity, aurora can be visible at much lower latitudes than usual, sometimes reaching the tropics. These celestial light shows connect us directly to the activity of our star. The Moon is drifting away from Earth. Every year, the Moon moves approximately 3.8 centimeters farther from Earth, a gradual recession caused by the transfer of rotational energy through tidal friction. The gravitational interaction between Earth and Moon creates tidal bulges in both bodies, and the friction of Earth's ocean tides acting against the seafloor gradually slows Earth's rotation. This lost rotational energy is transferred to the Moon, causing it to move into a slightly higher orbit. Laser ranging experiments using reflectors left on the lunar surface by Apollo astronauts allow us to measure this recession with remarkable precision. Billions of years ago, the Moon was much closer to Earth, looming larger in the sky and producing far more dramatic tides. As the Moon continues to recede, total solar eclipses will eventually become impossible, because the Moon will no longer be large enough in the sky to fully cover the Sun. We live in a fortunate era when our Moon exactly matches the apparent size of our Sun during these cosmic alignments. The dark side of the Moon is not always dark. The far side of the Moon, often incorrectly called the dark side, receives just as much sunlight as the side facing Earth. The term dark side is a misnomer arising from the fact that we never see this hemisphere from Earth, not from any lack of illumination. The Moon is tidally locked to Earth, meaning it rotates on its axis in the same time it takes to orbit Earth, so the same face always points toward us. During a new moon, when the near side is dark from our perspective, the far side is fully illuminated by the Sun. The far side of the Moon looks quite different from the near side, with fewer of the dark volcanic plains called Maria, and more heavily cratered highlands. This asymmetry may be related to differences in crustal thickness or the Moon's thermal history. The first images of the lunar far side were captured by the Soviet Luna 3 spacecraft in 1959, revealing a previously unseen world. You could fit all the planets between Earth and the Moon. The average distance between Earth and the Moon is about 384,000 kilometers. And remarkably, this is just enough space to line up all the other planets in the solar system end to end. Mercury, Venus, Mars, Jupiter, Saturn, Uranus and Neptune together span approximately 380,000 kilometers in diameter when measured equator to equator. This surprising coincidence illustrates both how far away the Moon is and how vast the gas giants truly are. Jupiter alone accounts for about 1/3 of this total, with its diameter of roughly 140,000 kilometers. The comparison puts the scale of the solar system into perspective, showing that even our nearest celestial neighbor is separated from us by an enormous gulf. Astronauts traveling to the Moon took about 3 days to cover this distance, moving at thousands of kilometers per hour. The emptiness of space is vast, even in our own cosmic backyard. Some moons are geologically active. Several moons in our solar system display surprising levels of geological activity, despite their small size and distance from the Sun. Jupiter's moon Io is the most volcanically active body in the solar system, with hundreds of active volcanoes constantly resurfacing the Moon with lava flows. This intense volcanism is driven by tidal heating, as Io's elliptical orbit causes it to be flexed by Jupiter's immense gravity, generating internal friction and heat. Saturn's moon Enceladus erupts geysers of water ice from cracks near its south pole, suggesting a subsurface ocean of liquid water. Neptune's moon Triton also shows signs of cryovolcanism, with nitrogen geysers observed during the Voyager 2 flyby. Even tiny moons that should have long ago cooled and become geologically dead continue to show evidence of ongoing activity. These active moons are prime targets in the search for environments that might support life beyond Earth. There may be hidden oceans larger than Earth's beneath icy moons. Several moons in the outer solar system are thought to harbor vast oceans of liquid water beneath their frozen surfaces. Europa, one of Jupiter's largest moons, may contain an ocean with twice the volume of all Earth's oceans combined, kept liquid by tidal heating from Jupiter's gravitational influence. Ganymede, the largest moon in the solar system, may also possess a subsurface ocean more than 100 kilometers deep. Saturn's moon Enceladus has confirmed plumes of water vapor erupting from its south pole, strongly suggesting a liquid water reservoir beneath the ice. These ocean moons represent some of the most promising locations in the solar system for finding conditions suitable for life. The presence of liquid water, combined with potential energy sources and chemical nutrients, creates environments where microbial life might theoretically exist. Future missions aim to sample these hidden oceans and search for signs of biology in the depths of these distant worlds. There are moons covered in ice geysers. Saturn's tiny moon Enceladus shoots spectacular jets of water ice and vapor hundreds of kilometers into space from the Tiger Stripe fractures near its south pole. These geysers contain not just water but also salts and organic molecules, material that appears to originate from a subsurface ocean in contact with the moon's rocky core. The plumes are so powerful that they contribute material to Saturn's E-ring, the outermost major ring in the Saturnian system. Spacecraft have flown through these plumes, capturing samples that reveal the chemistry of the hidden ocean below. The presence of hydrothermal activity at the ocean floor, suggested by the chemical composition of the plumes, would provide energy and nutrients that could potentially support microbial life. Triton, Neptune's largest moon, also displays geyser-like eruptions, though these are thought to be driven by nitrogen rather than water. These cosmic fountains offer tantalizing glimpses into the hidden worlds beneath icy surfaces. There are moons with atmospheres thicker than Earth's. Saturn's moon Titan is unique in the solar system for possessing a dense atmosphere, with surface pressure about 50% higher than Earth's at sea level. This thick blanket of mostly nitrogen with traces of methane and other hydrocarbons completely obscures the surface from view in visible light. Unlike Earth's atmosphere, Titan's lacks significant oxygen, but it contains complex organic molecules formed by sunlight interacting with methane. Beneath the thick haze, Titan has lakes and seas of liquid methane and ethane, the only known stable bodies of liquid on a surface other than Earth. The Huygens probe landed on Titan in 2005, revealing a landscape shaped by liquid erosion and deposits of organic material. Titan's chemistry is sometimes compared to a frozen version of early Earth, before life transformed our atmosphere. This moon represents one of the most intriguing destinations in the solar system for understanding prebiotic chemistry and the potential for exotic forms of life. Scientists believe it can rain solid diamonds on other worlds. Deep within the ice giant planets Uranus and Neptune, conditions may be extreme enough to convert carbon from methane into solid diamonds that rain down through the planetary interiors. Laboratory experiments have replicated the extreme pressures and temperatures found inside these planets, and successfully produced tiny diamonds from hydrocarbon compounds. As diamonds are denser than the surrounding material, they would sink toward the planetary core, potentially accumulating in layers of crystalline carbon. Some hot Jupiter exoplanets with carbon-rich atmospheres might experience similar diamond precipitation, creating worlds where gemstones fall from the sky. The conditions required suggest that diamond rain could be occurring right now inside planets throughout the galaxy, making diamonds far more common on cosmic scales than they are on Earth. While we may never see this phenomenon directly, the physics suggests that diamond rain is a real feature of certain planetary environments. These alien worlds could contain more diamonds than all the carbon on Earth, transformed into crystalline form. Rogue planets drift through space without a star. Not all planets are anchored to stellar systems. Some wander freely through the galaxy, unbound to any star. These rogue planets may have been ejected from their original star systems through gravitational interactions with other planets or passing stars. Estimates suggest there could be billions of rogue planets in our galaxy alone, perhaps even outnumbering the stars themselves. Despite lacking a sun to warm them, some rogue planets might retain enough internal heat to maintain liquid water beneath thick ice shells. If they carried substantial atmospheres, the greenhouse effect could potentially keep their surfaces habitable, even in the cold of interstellar space. Detecting rogue planets is extremely difficult because they emit no light of their own and reflect none from a parent star. Astronomers have discovered some candidates through gravitational microlensing, where a rogue planet briefly magnifies the light of a background star as it passes in front. Some planets orbit so close to their stars, they glow red-hot. Hot Jupiters are a class of exoplanets that orbit extremely close to their host stars, sometimes completing an orbit in just a few Earth days. These planets receive so much stellar radiation that their atmospheres can reach temperatures of 2000 degrees or more, hot enough to glow visibly in infrared and sometimes even visible light. The day side of these tidally locked worlds can be nearly as hot as some red dwarf stars, while the night side remains in perpetual darkness and relative coolness. Astronomers have detected the thermal emission from hot Jupiters directly, mapping temperature variations across their surfaces. Some ultra-hot Jupiters have atmospheres so extreme that molecules are torn apart on the day side and recombine on the cooler night side. These bloated, scorched worlds were among the first exoplanets discovered because their close orbits make them easier to detect. The extreme conditions on hot Jupiters push our understanding of planetary atmospheres into new regimes. Astronomers have found a planet where it rains glass. The exoplanet HD 189733b, located about 63 light-years from Earth, appears to experience a weather phenomenon stranger than any on our world. Sideways rain made of molten glass. This cobalt blue planet has an atmosphere containing silicate particles, which at the extreme temperatures present would condense into droplets of liquid glass. Fierce winds exceeding 7,000 kilometers per hour would whip these glass droplets horizontally across the planet's face at tremendous speeds. The beautiful blue color of this world comes not from water oceans, as on Earth, but from the scattering of light by silicate particles in the atmosphere. Temperatures on HD 189733b can reach over 1000 degrees Celsius, far too hot for water to exist in liquid form. Despite its Earth-like color, this planet represents one of the least hospitable environments ever discovered. The discovery of glass rain demonstrates how exotic weather conditions can become on alien worlds. There are planets with 2 or more suns. Circumbinary planets orbit around both stars in a binary star system, experiencing double sunrises and sunsets that would create alien skyscapes beyond anything seen on Earth. The famous fictional planet Tatooine from Star Wars, with its twin suns, has real analogues that have been discovered by the Kepler Space Telescope. The first confirmed circumbinary planet, Kepler 16b, orbits a pair of stars about 200 light-years from Earth. Living on such a world would mean experiencing complex lighting conditions, with varying shadows and day lengths, as the 2 suns move at different rates. Some binary star systems are close enough that their stars nearly touch, while others are separated by distances comparable to planetary orbits. Planets can also exist in systems with 3 or more stars, creating even more complex orbital dynamics and lighting. These alien solar systems challenge our Earth-centric assumptions about what planetary environments can look like. Planets can orbit in opposite directions around the same star. Astronomers have discovered exoplanets with retrograde orbits, meaning they orbit their stars in the opposite direction from the star's rotation. In our solar system, all major planets orbit the Sun in the same direction, a consequence of forming from a shared disk of material that rotated in one direction. Retrograde exoplanets must have had their orbits dramatically altered at some point, likely through gravitational interactions with other planets or close encounters with passing stars. Some hot Jupiters have been found in retrograde or highly tilted orbits, suggesting violent pasts filled with planetary rearrangements. These misaligned orbits tell stories of chaotic gravitational histories that scrambled the original orderly arrangement of planets. The discovery of retrograde planets has forced astronomers to reconsider theories of planetary formation and evolution. Not all planetary systems evolved as peacefully as our own solar system appears to have done. Some comets come from beyond the solar system. In 2017, astronomers detected the first confirmed interstellar visitor to our solar system, an object named Oumuamua that passed through on a trajectory that could not have originated from any location within our Sun's gravitational domain. This elongated visitor was traveling too fast to be captured by the Sun and quickly departed back into interstellar space. A second interstellar object, Comet Borisov, was discovered in 2019, displaying a more typical cometary appearance with a coma and tail. These interstellar visitors offer glimpses of material from other star systems, potentially carrying information about planetary formation around distant suns. Scientists estimate that interstellar objects pass through the inner solar system several times per year, though most go undetected. The discovery of these cosmic travelers has opened a new field of study, as each interstellar object represents a sample of another stellar neighborhood. Future missions may attempt to intercept and study such objects before they leave our solar system. Some asteroids are packed with precious metals. Certain asteroids, particularly metallic M-type asteroids, contain vast quantities of iron, nickel, platinum, and other valuable metals that could potentially be mined in the future. A single metallic asteroid a kilometer or 2 across could contain more platinum than has ever been mined in all of human history. These metal-rich asteroids are thought to be the cause of failed protoplanets that were shattered by collisions early in solar system history, exposing their iron interiors. The asteroid Psyche, target of a NASA mission, is believed to be almost entirely metallic and could contain iron worth far more than the current global economy. While asteroid mining remains technologically challenging and economically uncertain, the potential resources in the asteroid belt dwarf anything available on Earth. Beyond precious metals, asteroids also contain water, carbon compounds, and other materials that could support future space exploration and colonization. The riches of the asteroid belt wait patiently for humanity to develop the capability to harvest them. There are asteroids with their own tiny moons. Not just planets can have moons. Many asteroids in the solar system are accompanied by their own small natural satellites. The first asteroid moon was discovered in 1993 when the Galileo spacecraft passed by asteroid Ida and photographed a tiny moon, later named Dactyl, orbiting it. Since then, dozens of asteroid moons have been found, revealing that binary and even triple asteroid systems are relatively common. These small companions are thought to form through collisions that eject material into orbit, or through gravitational capture of nearby objects. Studying asteroid moons provides valuable information about the masses and densities of their parent bodies, which is difficult to determine otherwise. Some asteroids have been found to be contact binaries, where two objects orbit so closely that they touch and form a peanut or snowman shape. The NASA DART mission successfully demonstrated that an asteroid's orbit could be changed by impacting its small moon, a technique that could someday be used to defend Earth from hazardous objects. The Oort cloud holds trillions of icy objects. Surrounding our solar system at distances of up to 2 light-years from the Sun is the Oort cloud, a vast spherical shell of icy bodies left over from the formation of the planets. This distant reservoir is thought to contain trillions of cometary nuclei, frozen relics from the early solar system that were ejected to the outer reaches by gravitational interactions with the giant planets. Occasionally, a passing star or galactic tide perturbs one of these icy objects, sending it falling inward toward the Sun, where it develops a coma and tail and becomes a long-period comet. No spacecraft has ever traveled far enough to directly observe the Oort cloud, and individual objects within it are far too small and dim to detect from Earth. The existence of the Oort cloud is inferred from the orbital characteristics of long-period comets that appear to originate from all directions in the sky. This distant frontier of the solar system represents one of the last great unexplored regions under the Sun's gravitational influence. Comets have been visiting Earth for billions of years. Throughout the history of our planet, comets have periodically plunged into the inner solar system, their icy bodies heated by the Sun to produce spectacular displays visible from Earth. Some scientists believe that comet impacts in the early solar system may have delivered significant amounts of water and organic molecules to Earth, potentially contributing to the conditions that made life possible. Ancient civilizations observed comets with a mixture of awe and fear, often interpreting them as omens of disaster or divine messages. The regularity of some comets, like Halley's Comet, which returns every 76 years or so, has been tracked for centuries. Meteor showers occur when Earth passes through the debris trails left by comets, producing streaks of light as tiny particles burn up in our atmosphere. Comets are essentially time capsules from the birth of the solar system, preserving pristine material from 4.5 billion years ago. These cosmic wanderers connect us to the earliest epochs of our solar system's history. Spacecraft have left the solar system and entered interstellar space. Voyager 1 and Voyager 2, launched in 1977, have become the first human-made objects to enter interstellar space, the region beyond the influence of the Sun's solar wind. Voyager 1 crossed this boundary in 2012, followed by Voyager 2 in 2018. Both spacecraft continue to communicate with Earth, sending back data about the conditions in interstellar space, even though their signals take over 22 hours to reach us. At their current speeds, the Voyagers will not reach the vicinity of another star for tens of thousands of years, illustrating the vast emptiness between stellar systems. Each Voyager carries a golden record containing sounds and images from Earth, a message in a bottle cast into the cosmic ocean for any future finder. The nuclear power sources on both spacecraft are slowly decaying, and they will eventually fall silent, sometime in the late 2020s or early 2030s. These distant ambassadors of humanity continue their lonely journeys into the unknown. You can see the International Space Station with the naked eye. The International Space Station orbits approximately 400 kilometers above Earth and is easily visible as a bright moving point of light crossing the night sky. With its large solar panels reflecting sunlight, the station can appear as bright as Venus, making it the third brightest object in the night sky after the Sun and Moon. A typical pass takes several minutes as the station travels from horizon to horizon at over 27,000 kilometers per hour. Timing websites and apps can predict exactly when the station will be visible from your location, allowing anyone to watch this outpost of humanity sailing overhead. Since its construction began in 1998, the space station has been continuously occupied, with astronauts and cosmonauts living and working in microgravity. Seeing the station cross the sky is a reminder that right now, above us, a handful of humans are orbiting Earth every 90 minutes. Spotting this feat of international cooperation is as simple as looking up at the right moment. There are places in space where gravity cancels out. Lagrange points are special locations in space where the gravitational pulls of two large bodies, combined with the centrifugal force of orbital motion, create stable or semi-stable equilibrium points. At these locations, objects can maintain their position relative to both bodies without expending significant fuel. The Sun-Earth system has 5 Lagrange points, with the James Webb Space Telescope stationed at the second Lagrange point, roughly 1.5 million kilometers from Earth, in the direction away from the Sun. This position allows the telescope to keep its sunshield between itself and both the Sun and Earth, maintaining the extreme cold needed for infrared observations. Other Lagrange points have been proposed as locations for future space stations, fuel depots, or astronomical observatories. The mathematics of these equilibrium points was worked out by the Italian-French mathematician Joseph-Louis Lagrange in the 18th century. These gravitational sweet spots represent efficient locations from which to observe the cosmos or stage future missions. Humans have sent music into interstellar space. The Voyager Golden Records, attached to both Voyager spacecraft, contain a selection of music from around the world alongside greetings in multiple languages and sounds of Earth. The music ranges from Beethoven and Mozart to Chuck Berry, and traditional music from many cultures, offering any future finder a taste of human artistic expression. These gold-plated copper records were designed to be playable for billions of years, protected from cosmic erosion by their aluminium covers. Instructions etched on the covers explain how to play the records using a stylus also included on the spacecraft. The records represent humanity's attempt to communicate across not just space but time, sending a message that may outlast our civilization by eons. So far, these records have traveled over 20 billion kilometers from Earth, the farthest any human-created music has ever gone. Somewhere in the darkness between the stars, Beethoven's Fifth Symphony drifts silently outward on an eternal journey. Rovers have explored Mars for years without human contact. Several robotic rovers have rolled across the Martian surface, conducting scientific investigations far from any direct human presence. The Opportunity rover operated for nearly 15 years, far exceeding its planned 90-day mission before finally succumbing to a global dust storm in 2018. Curiosity has been exploring Gale Crater since 2012, analyzing rocks and searching for signs of past habitable conditions. The Perseverance rover, which landed in 2021, is collecting rock samples that a future mission will return to Earth for detailed analysis. These rovers are essentially robotic geologists, equipped with cameras, spectrometers, and drilling tools to study the Martian environment in ways impossible from orbit. Communication delays of up to 20 minutes mean that the rovers must operate with significant autonomy, navigating hazards and making decisions without real-time human input. These tireless explorers have transformed our understanding of Mars from a mysterious red dot to a world with a complex geological history. The coldest place in the universe is colder than empty space. The cosmic microwave background radiation gives empty space a baseline temperature of about 2.7 Kelvin, or roughly -270 degrees Celsius. However, astronomers have found locations in space that are even colder than this cosmic minimum. The Boomerang Nebula, a cloud of gas expelled by a dying star about 5,000 light-years from Earth, has regions that reach temperatures below 1 Kelvin. The rapid expansion of gas from the central star caused extreme cooling, similar to how compressed air cools when released from a canister. At these temperatures, molecular motion nearly ceases, approaching the theoretical limit of absolute zero. The Boomerang Nebula is currently the coldest known natural place in the universe, making it colder than the void of intergalactic space itself. Scientists have created even colder temperatures in laboratories on Earth, but naturally occurring cold spots like this nebula remain extraordinary discoveries. The vacuum of space can boil your blood. In the near-total vacuum of space, the absence of atmospheric pressure would cause dramatic and fatal effects on an unprotected human body. At normal body temperature, water boils when pressure drops below a certain threshold, meaning that saliva on the tongue and moisture in the lungs would begin to vaporize almost immediately upon exposure to vacuum. Blood circulating close to the surface of skin would not instantly boil because it remains under pressure within blood vessels, but gases dissolved in body tissues would begin to form bubbles in a process similar to decompression sickness. Consciousness would be lost within about 15 seconds as oxygen depleted from the brain. Contrary to Hollywood depictions, a person would not freeze instantly or explode. Instead, the body would swell as internal gases expanded, but skin is strong enough to prevent rupture. Survival might be possible for a minute or two if quickly returned to pressure, though permanent injury would likely result. The vacuum of space is an unforgiving environment that requires complete protection for human survival. Space has no true up or down. On Earth, gravity provides a clear sense of direction, pulling everything toward the planet's center and defining a universal down. In the freefall environment of space, this reference disappears, leaving no objective way to define up, down, left, or right. Astronauts aboard the International Space Station often describe the disorientation of working in an environment where floors and ceilings are arbitrary designations. The interior of the station is designed with visual cues to help maintain orientation, but crew members can work equally well upside down by earthly standards. When looking at images of space, the orientation is entirely dependent on how the photographer chose to frame the shot. Galaxies have no inherent top or bottom, and even the solar system's plane is only a reference relative to the sun's equator. The universe itself has no preferred direction, a property called isotropy that is one of the fundamental assumptions of cosmology. Space is not completely empty. The vacuum of space is not truly empty, but rather filled with a thin soup of particles, radiation, and fields. The interstellar medium contains roughly 1 atom per cubic centimeter on average, mostly hydrogen with some helium and trace heavier elements. This diffuse gas and dust fills the space between stars, sometimes concentrating into denser molecular clouds where new stars are born. Even in the vast voids between galaxies, the intergalactic medium contains trace amounts of matter, heated to millions of degrees by shock waves and cosmic phenomena. Beyond ordinary matter, space is permeated by the cosmic microwave background radiation, a bath of photons, left over from the Big Bang. Magnetic fields thread through galaxies and galaxy clusters, while dark matter and dark energy fill the cosmos in ways we still do not fully understand. What we call empty space is actually a dynamic environment filled with phenomena invisible to the naked eye. Cosmic rays pass through your body every second. High-energy particles from across the universe constantly bombard Earth's atmosphere, creating showers of secondary particles that reach the surface and pass harmlessly through our bodies. These cosmic rays originate from sources including the Sun, supernovae, and the supermassive black holes at the centers of distant galaxies. Most are protons or atomic nuclei traveling at nearly the speed of light, carrying energies that can exceed anything produced by human-made particle accelerators. When they strike the upper atmosphere, they create cascades of secondary particles, some of which reach ground level. The average person is hit by several cosmic ray particles every second, though most cause no detectable harm, because they pass through without interacting. At higher altitudes, such as during aeroplane flights, the cosmic ray exposure increases noticeably. For astronauts outside Earth's protective magnetic field, cosmic ray exposure represents a significant health concern on long-duration missions to the Moon or Mars. There are clouds of alcohol in space. Astronomers have discovered vast molecular clouds in space that contain significant quantities of ethyl alcohol and methyl alcohol among other organic compounds. One such cloud, located near the center of the Milky Way in a region called Sagittarius B2, contains enough ethyl alcohol to fill hundreds of billions of pints, if it could somehow be collected. These cosmic cocktails form through chemical reactions on the surfaces of dust grains in cold molecular clouds, where simple molecules combine into more complex organic structures. The alcohol is spread so thinly through the cloud that you could never actually drink it. There are still only a few molecules per cubic meter of space. Along with alcohol, these clouds contain many other organic molecules that could be considered precursors to life. The discovery of complex molecules in interstellar space suggests that the chemical building blocks for life may be widespread throughout the galaxy. The cosmos is essentially brewing ingredients that could someday contribute to biology on distant worlds. There are giant clouds of gas larger than galaxies. Between galaxies and within galaxy clusters, enormous clouds of hot gas stretch across millions of light-years, vastly exceeding the size of individual galaxies. This intracluster medium can contain more mass than all the stars in the cluster's galaxies combined, heated to temperatures of tens of millions of degrees by gravitational collapse and shock waves. These superheated gas clouds glow in X-rays, making them visible to space-based X-ray telescopes even though they are invisible to optical observations. The gas in these cosmic reservoirs represents material that never collapsed into stars, remaining in a diffuse state between the gravitationally bound galaxies. Filaments of gas connecting galaxy clusters can extend for hundreds of millions of light-years, forming part of the cosmic web that underlies the large-scale structure of the universe. Some of this hot gas cools and falls into galaxies, fueling future star formation, while other portions remain suspended in intergalactic space. These vast gas clouds are among the largest discrete structures in the universe. Every atom in your body was forged in a star. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of every biological molecule, all of these elements were created inside stars that lived and died billions of years ago. The Big Bang produced only hydrogen, helium, and traces of lithium. Everything heavier was synthesized later through nuclear fusion in stellar cores. Lightweight elements like carbon and oxygen are produced in the cores of ordinary stars like the Sun, while heavier elements up to iron are forged in the more extreme conditions of massive stars. Elements heavier than iron, including gold, platinum, and uranium, require even more violent processes like supernova explosions or neutron star mergers to form. When stars explode at the end of their lives, they scatter these freshly forged elements across space, enriching the interstellar medium for future generations of stars and planets. You are literally made of stardust, assembled from atoms that were once part of stellar furnaces. Every breath you take, every thought you have, depends on the deaths of ancient stars. gold was created in the collision of neutron stars. The heavy elements that make up precious metals like gold and platinum are created through a process called rapid neutron capture, which requires the extreme conditions found only in the most violent cosmic events. For decades, scientists debated where in the universe these conditions might exist, with supernovae being the leading candidate. In 2017, the detection of gravitational waves from a neutron star merger, combined with electromagnetic observations of the resulting explosion, provided direct evidence that these cosmic collisions produce vast quantities of heavy elements. The kilonova that followed the merger glowed with the distinctive signatures of newly created gold, platinum, and other R-process elements. Calculations suggest that a single neutron star merger can produce several Earth masses worth of gold, scattering it across space to eventually be incorporated into new planetary systems. Every piece of gold on Earth was likely forged in one or more neutron star collisions that occurred before our solar system formed. Your gold wedding ring has a more violent origin than you might have imagined. The universe creates elements through cosmic alchemy. The transformation of simple elements into complex ones is a form of cosmic alchemy that occurs naturally in stars and violent cosmic events. Hydrogen, the simplest element, is gradually transmuted into helium through nuclear fusion in stellar cores, releasing the energy that makes stars shine. Further fusion reactions build heavier elements step by step, with each stage requiring higher temperatures and pressures. This process of stellar nucleosynthesis is responsible for filling the periodic table with elements that did not exist in significant quantities after the Big Bang. Unlike the failed efforts of medieval alchemists to turn lead into gold, the universe accomplishes elemental transmutation on scales that dwarf anything humans could imagine. The cosmic abundance of elements, with hydrogen and helium dominating and heavier elements becoming progressively rarer, reflects the history of stellar processing over billions of years. We live in a universe that has been self-enriching since the first stars ignited, creating ever more complex atomic building blocks. We can see galaxies as they were billions of years ago. Because light travels at a finite speed, looking at distant objects means looking back in time. When astronomers observe a galaxy a billion light-years away, they see it as it appeared a billion years ago, when the light now reaching their telescopes first began its journey. The most distant galaxies visible to modern telescopes appear as they were over 13 billion years ago, when the universe was only a few 100 million years old. These infant galaxies look dramatically different from nearby mature galaxies, often smaller, bluer, and more irregularly shaped. By studying galaxies at different distances, astronomers can trace the evolution of galactic structure across cosmic time, essentially watching galaxies grow up. The James Webb Space Telescope has pushed our view even farther back in time, revealing some of the first galaxies to form after the Big Bang. Every image of the deep universe is a time machine, showing us the cosmos as it once was rather than as it is today. The night sky contains light from long-dead stars. Many of the stars we see twinkling in the night sky no longer exist, having exhausted their nuclear fuel and exploded or faded long before their light reached Earth. A star 1,000 light-years away might have died 900 years ago, but we will continue seeing its light for another century before it winks out from our perspective. The most distant individual stars visible to the naked eye are thousands of light-years away, meaning their light has been traveling for millennia. Even the relatively nearby star Betelgeuse, which may explode as a supernova at any time, is about 700 light-years distant. It could have already exploded during the Middle Ages without us knowing yet. This time lag between cosmic events and our observation of them creates a strange relationship between what we see and what currently exists. The night sky is essentially a museum of light, displaying images from various points in the past simultaneously. We gaze upward at a cosmic history lesson written in starlight. The universe may be infinite in size. While we can only observe the portion of the universe from which light has had time to reach us, the actual universe may extend far beyond this observable horizon, potentially to infinity. Measurements of the cosmic microwave background suggest that space is geometrically flat to a high degree of precision, which is consistent with, but does not prove an infinite extent. If the universe is truly infinite, it contains an infinite number of galaxies, stars, and potentially an infinite number of planets with life. The concept of infinity creates strange philosophical implications, including the possibility that somewhere in an infinite cosmos, exact duplicates of you and everything on Earth might exist. Whether the universe is finite but unbounded, like the surface of a sphere, or truly infinite remains one of the deepest unsolved questions in cosmology. The observable universe, with its radius of 46 billion light-years, may be just a tiny bubble in a vastly larger or endless expanse. Infinity remains beyond our ability to directly observe or confirm. The oldest light in the universe is almost 14 billion years old. The cosmic microwave background radiation represents the oldest electromagnetic radiation that can be detected, released about 380,000 years after the Big Bang, when the universe first became transparent. Before this epoch of recombination, the universe was an opaque fog of ionized plasma that scattered light, preventing photons from traveling freely. When atoms first formed, and the universe cooled enough for electrons to bind to nuclei, light was suddenly free to propagate across space. That ancient light has been traveling ever since, cooling and stretching to become the microwave glow we detect today, at a temperature of about 2.7 Kelvin. Precision measurements of the cosmic microwave background have revealed the age of the universe to be approximately 13.8 billion years. Nothing older than this primordial glow can be directly observed with electromagnetic radiation, though gravitational waves might eventually allow us to probe even earlier epochs. The cosmic microwave background represents the edge of our observational horizon in time. Supermassive black holes can control entire galaxies. Despite containing only a tiny fraction of a galaxy's total mass, the supermassive black hole at its center can profoundly influence the entire galactic system. When actively consuming matter, these black holes release enormous amounts of energy that can heat surrounding gas and prevent it from cooling and forming new stars. This feedback mechanism appears to regulate the size of galaxies, explaining why the largest galaxies stop growing rather than becoming infinitely massive. Powerful jets launched by active supermassive black holes can extend far beyond the galaxy itself, stirring the intergalactic medium and affecting the evolution of neighboring galaxies. Observations show a tight relationship between the mass of a central black hole and the properties of its host galaxy, suggesting that they co-evolve together. The black hole at the center of the Milky Way Sagittarius A star is currently dormant but has likely been active in the past. These gravitational engines help sculpt the galactic ecosystems in which stars and planets form. The largest black holes can hold entire solar systems inside them. The most massive black holes known, ultramassive black holes containing tens of billions of solar masses, have event horizons so vast that our entire solar system could fit inside them with room to spare. The black hole at the center of the galaxy TON 618 may contain 66 billion solar masses, with an event horizon spanning over 1,000 astronomical units. This means the distance from this black hole's center to its event horizon exceeds the distance from the Sun to far beyond Pluto's orbit. Despite their immense size, these black holes are not especially dense by black hole standards, because the density within the event horizon decreases as the black hole gets larger. Crossing the event horizon of such a massive black hole would initially feel almost peaceful, with tidal forces being relatively gentle near the boundary. Only deeper inside would the traveler be torn apart by the ever-increasing gravitational gradients. The sheer scale of these cosmic giants challenges our ability to comprehend spatial dimensions. Quasars are among the brightest objects in the universe. When supermassive black holes at the centers of distant galaxies actively consume surrounding matter, they can produce quasars, beacons of light visible across billions of light-years. A single quasar can outshine its entire host galaxy by a factor of 1,000, emitting as much energy as trillions of suns. This incredible luminosity comes from the accretion disk around the black hole, wherein falling matter is heated to extreme temperatures before crossing the event horizon. When first discovered in the 1960s, quasars appeared as point-like sources similar to stars, leading to their name as quasi-stellar objects. Their true nature as the luminous cores of distant galaxies was only understood later. The most distant quasars are observed as they existed within the first billion years after the Big Bang, providing windows into the early universe. Quasars represent the universe's ultimate powerhouses, converting matter into energy with an efficiency far exceeding any other known process. Some galaxies have two supermassive black holes at their centers. When galaxies merge, their central supermassive black holes are brought together, initially orbiting within the merged galactic core, before eventually coalescing. During this process, which can last hundreds of millions of years, the galaxy temporarily contains two supermassive black holes at its center. Astronomers have observed several examples of binary supermassive black holes at various stages of their cosmic dance, separated by distances ranging from thousands of light-years down to just a few light-years. As the black holes spiral closer together, they emit gravitational waves at frequencies that future space-based detectors may be able to observe. The final merger of two supermassive black holes would be among the most energetic events in the universe, releasing more energy in gravitational waves than all the stars in both galaxies combined. Studying binary supermassive black holes provides insight into both galaxy mergers and the physics of black hole coalescence. These gravitational duets are staging grounds for some of the most dramatic events in cosmic evolution. The universe might contain an infinite number of parallel realities. Some interpretations of quantum mechanics and certain cosmological theories suggest that our universe may be just one among an infinite number of parallel realities. The many worlds interpretation of quantum mechanics proposes that every quantum measurement causes the universe to split into multiple branches, each representing a different outcome. Inflationary cosmology leads some scientists to propose a multiverse where our observable universe is just one bubble in an eternally inflating sea, with other bubble universes having potentially different physical laws. String theory suggests a vast landscape of possible universes, each with its own configuration of extra dimensions and fundamental constants. These ideas remain highly speculative and are currently untestable by any known experimental method, placing them at the boundary between physics and philosophy. If the multiverse exists, there could be versions of reality where history took different turns, or where the laws of physics permit entirely different phenomena. The concept challenges our understanding of what it means for something to exist. The Big Bang created more than just matter. When the universe began, it did not merely produce the matter and radiation we observe today. It also created space, time, and the fundamental laws of physics themselves. Before the Big Bang, There was no space to expand into, and no time during which anything could happen. Both emerged together with the birth of the cosmos. The forces of nature, including gravity, electromagnetism, and the nuclear forces, assumed their current forms as the universe cooled in the moments after the initial expansion. The quantum fluctuations that occurred in the first instance of existence seeded the large-scale structure of the cosmos, determining where galaxies and voids would eventually form. What caused the Big Bang remains unknown, as our theories of physics break down at the initial singularity. The creation of existence itself, including the arena of space-time in which events occur, represents perhaps the ultimate mystery. We live within and are made of the products of this singular creative moment. There may be regions of the universe we can never observe. Due to the accelerating expansion of the universe driven by dark energy, there are regions of space that are forever beyond our reach, from which light will never have time to travel to us no matter how long we wait. The cosmic event horizon marks the boundary beyond which we can never receive information, as the expansion of space outpaces the speed of light. Galaxies that we can see today will eventually cross this horizon, fading from view as their light becomes infinitely redshifted. In the far distant future, observers in our galaxy will see an empty sky with no evidence that other galaxies ever existed. The universe accessible to us is shrinking, even as the actual universe continues to expand. What lies beyond the cosmic horizon is forever unknowable by direct observation, though we assume it is similar to the universe we can see. This fundamental observational limit means that vast regions of existence may remain permanently hidden from human knowledge. Gravity waves ripple through spacetime like ripples on a pond. Gravitational waves are disturbances in the fabric of spacetime itself, propagating outward from violent cosmic events at the speed of light. First predicted by Einstein's general relativity in 1916, these waves were directly detected for the first time in 2015 by the LIGO observatories. The waves stretch and compress space perpendicular to their direction of travel, though the effect is incredibly tiny, typically changing distances by less than the diameter of a proton. The strongest gravitational waves detectable on Earth are produced by merging black holes and neutron stars, events that release staggering amounts of energy into spacetime oscillations. As gravitational waves pass through space, they carry information about their sources, opening a new window for studying the cosmos that does not rely on electromagnetic radiation. The era of gravitational wave astronomy has already produced discoveries impossible with traditional telescopes, including the detection of black holes in unexpected mass ranges. The universe rings with these ripples in spacetime, a symphony of cosmic vibrations we are only now learning to hear. The universe may have existed before the Big Bang. While the Big Bang marks the beginning of our current cosmic epoch, several theoretical frameworks suggest that something may have existed before it. Cyclic models of cosmology propose that the universe goes through endless cycles of expansion and contraction, with each Big Bang being preceded by a big crunch from a previous cycle. The ekpyrotic scenario, derived from string theory, suggests our universe began when two higher dimensional structures called branes collided. Conformal cyclic cosmology proposes that the distant future of one universe smoothly transitions into the Big Bang of another. These pre-Big Bang scenarios remain highly speculative, as any information about prior states would have been erased by the extreme conditions of the Big Bang itself. The question of what came before the beginning may be fundamentally unanswerable, or it may require new physics to address. Time itself may have had a different character before the Big Bang, or the concept of before may not apply at all. Somewhere in the universe, a planet like Earth may be waiting. With billions of stars in the Milky Way alone, and billions of galaxies in the observable universe, the number of planets in existence is almost beyond comprehension. Statistical estimates suggest that Earth-like planets in habitable zones, where liquid water could exist on the surface, may number in the tens of billions in our galaxy alone. Some of these worlds may share similar size, composition, and temperature with Earth, orbiting stable stars that have shone for billions of years. Whether any of these potentially Earth-like worlds actually harbor life, or have ever developed intelligent civilizations, remains one of the great unanswered questions in science. The search for biosignatures in the atmospheres of exoplanets is now technologically feasible, and future telescopes may detect signs of life on distant worlds within our lifetimes. The discovery of another Earth, particularly one with signs of life, would transform our understanding of our place in the cosmos. Somewhere out there, a blue marble much like our own may be quietly orbiting its star. Life on Earth may have originated from the stars. The theory of panspermia suggests that life, or at least the complex organic molecules necessary for life, may have been delivered to Earth from space. Comets and asteroids contain amino acids, nuclear bases, and other organic compounds that are essential building blocks for biology. Early Earth was bombarded by these celestial objects during the late heavy bombardment period, potentially seeding our planet with the raw materials for life. Some versions of panspermia propose that microbial life itself could survive the journey through space, protected within rocky material ejected from other planets. Experiments have shown that certain microorganisms can survive the harsh conditions of space, including vacuum, radiation, and extreme temperature fluctuations. If panspermia is true, life on Earth may be part of a cosmic distribution of biology that spreads from world to world across the galaxy. Whether life originated here or arrived from elsewhere, we are connected to the wider cosmos by our very existence. The building blocks of life exist throughout the universe. Astronomers have detected complex organic molecules in interstellar space, meteorites, comets, and the atmospheres of moons and planets across our solar system. Amino acids, the components of proteins, have been found in meteorites that have fallen to Earth, demonstrating that these molecules form naturally in space. The molecular clouds from which stars and planets form contain a rich chemistry of carbon compounds, sugars, and other organic precursors. Titan's atmosphere is thick with organic molecules, while the plumes of Enceladus contain the ingredients that life on Earth requires. These discoveries suggest that the chemistry of life is not unique to our planet, but rather a common outcome of cosmic processes. The same carbon-based chemistry that powers life on Earth appears to be widespread throughout the galaxy, increasing the plausibility that life could arise elsewhere. The universe seems to be fundamentally conducive to the formation of complex organic matter. Water may be more common in the universe than we once thought. Water, the essential medium for life as we know it, appears to be surprisingly abundant throughout the cosmos. Ice has been found on moons, dwarf planets, asteroids, and in the polar craters of Mercury and our own moon. The moons of Jupiter and Saturn harbor vast subsurface oceans of liquid water, potentially containing more water than all of Earth's oceans combined. Water vapor has been detected in the atmospheres of exoplanets and in the protoplanetary disks around young stars. Even interstellar space contains water molecules, formed through chemistry on dust grains and in molecular clouds. The hydrogen that makes up water is the most abundant element in the universe, while oxygen is produced abundantly by dying stars. The ubiquity of water increases the probability that habitable conditions may exist on countless worlds throughout the galaxy. The cosmic prevalence of this essential molecule suggests that the conditions for life may be far more common than we once imagined. And now the quiet wonders of space begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths. From the expanding fabric of the universe to the swirling disks around black holes. From the fiery hearts of giant stars to the frozen oceans beneath icy moons. You have explored the hidden rhythms of pulsars, the slow dance of colliding galaxies, and the mysteries that stretch across billions of light years. You are part of this story, not just an observer, but the story itself. Every atom in your body was forged in ancient stars. The iron in your blood, the oxygen you breathe, the carbon in your bones, all of it was born in stellar furnaces and scattered across cosmic distances. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle expansion of the universe itself, like the patient drift of galaxies through the cosmic web. Tonight, as you rest, the cosmos continues its ancient dance. Galaxies drift through the dark, stars ignite and fade, and somewhere beyond our cosmic horizon, mysteries we may never understand unfold in silence. You are a small, warm presence within this infinite expanse, peacefully resting among the wonders of existence. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that you are woven into something vast and beautiful. A universe that began before time and stretches toward eternity. Thank you for joining me on this journey through the wonders of space. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of science and our remarkable universe. There are more wonders waiting. More secrets hidden in the fabric of space-time. More mysteries to drift through on quiet evenings. Rest well, and may the cosmos keep you company through the night. This has been Drowsy Discovery. Good night.